Okay, so let's go over the exam. This was exam 2. Do you want to go over it first, or do you have any questions? You want to talk about something specific? Um, did you think it was what you expected it to be, in terms of challenge and rigor? Were you prepared well for it? I know the last week before that I had some health issues, but hopefully we got caught up, and it seemed like most of the people did pretty well. So I'm just curious what people thought.
Yeah, it seemed to cover everything you did in class.
Okay. Did everybody feel prepared? Or not prepared enough?
Felt prepared.
Okay. Anybody else want to chime in? Okay, well, we'll do the best we can, but feel free to pipe in when you have some comments or questions. So let's go through the first one, which is short circuit and open circuit tests. So what I always recommend to everybody when you're doing this work is to just put what you're trying to solve for. And here's our base transformer equivalent circuit. And I'm going to put everything on one side of the transformer just to make it easier. Here's my R equivalent, my JX equivalent. Then I have my core, my JXM for magnetizing. And then I have my transformer. And this is the equivalent circuit that I'm trying to solve for. This is essentially, excuse me, what I'm trying to get. So we have two tests. And if you recall, when we do the open circuit test, the voltage applied is very, well, the voltage applied is nominal, but the current applied is almost negligible. It's very, very small. So what happens is my voltage drop across here, those two elements, because the current is so small, is pretty small to the point where it's negligible. So my open circuit characteristic is going to essentially show me my core resistance and my magnetizing resistance, and that's it. There's nothing else to it. So when I do my open circuit characteristic, I've got an applied voltage, V open circuit. I have a current, I open circuit. And when you're in the field, it's not always easy to get the angular difference between the voltage and the current. But what is easy or easier is to get the open circuit power that's in there. With this information, we have enough to go ahead and calculate the impedances. So when we are dealing with elements that are in parallel with each other, it's much easier to deal with admittances. So we're going to solve for Y open circuit, which is equal to my current. That's theta open current. And remember, this is a negative value because this is a lagging power factor. It's an inductive circuit. It is lagging. And then we divide this by V open circuit. And since we don't have a reference point, we normally will pick our voltage reference point to be zero. And we have those values there. So the only thing we need to do, or that we don't have, because we can check and see, I've got my open circuit current. I have my open circuit voltage. I do not know my theta open circuit, so I have to draw a power triangle. Because the angle between P and S is the impedance angle, but that's also the angle that's between V and I. So this is my open circuit power. And this is my open circuit S. This is theta open circuit. So theta open circuit is equal to the inverse cosine of P open circuit over S open circuit. Once I have that, I can substitute that into my my values here. Let me see if I can zoom out just a little bit. And this becomes, so let's cheat this up over here because I'm running out of space. So Y open circuit, once I do the calculation, is going to be 1 over R sub C minus 1 over JXM. So when you break those down into rectangular coordinates, you'll see that your R sub C term, you can obtain that by inverting the real part of Y open circuit. And your imaginary part, you get that by inverting and getting your magnetizing reactance. Now, does anybody want to see any numbers with that, or is the equation sufficient? Can you still hear me?
Personally,
Sorry, I didn't hear.
that I'm personally good with the equation.
Okay.
Hey, Mayor.
Okay. Any questions or any confusion on this one? This wasn't intended to be a tricky one. This was just, we had done a bunch of these. So this was hopefully a fairly straightforward to get the open circuit test. The short circuit test is very similar. I'm going to draw it over here because I'm running out of space. So my short circuit test is just going to give me my resistance and my inductance. And because the voltage is so low, the applied voltage is so low, that there's hardly any current that goes through. Well, there's two big things. The voltage is very low, and RC and JXM should be very high. So because of that, we can assume that there's no current, or essentially no current going through those, that they are open circuits. And when we do that, all we're left with is a circuit that looks like this. Similar deal, we have a plus minus V short circuit. We have a current in here, I short circuit. And we have a P short circuit that we have for data. So we're going to go ahead and solve for Z short circuit, which is equal to my V short circuit at an angle of 0. Same rules that applied for the open circuit. We apply for the short circuit. We're going to divide that by I short circuit, whose angle is minus theta short circuit. And just like we did over here, we're solving for our short circuit angle, P short circuit, S short circuit, and this is theta short circuit. And how do you solve for theta short circuit? It's exactly the same approach, just using different numbers. And that was the process to solve this problem. I think most people got this right. A couple people, and just as a just to check your results. If you have a transformer and if your R and your X are fairly high, like if you're pushing 20 amps through something that has, let's say 5 or 10 ohms of resistance, 20 amps times something that's 5, you're going to be dropping 100 volts. This is only a 240 volt transformer. So if you're pushing almost 21 amps through a 240 on the 240 volt side of the transformer, what you're going to find is you're going to have a pretty significant voltage drop on that. So you can't have crazy high impedances. And so if you're getting R's and X's that are in the 5 and 10 and 20 range, you probably want to go back and double check. Same thing with the R sub C and JX sub M. If your R sub C's and JX sub M's aren't in the K range, so remember it's 240 divided by whatever the RC value is. If that's only a couple ohms, you're getting a lot of power that's being dissipated through the core of the transformer. So your R sub C and your JXM values should be very, very high. And most transformers today that when we analyze them, we actually assume that they're going to be treated as open circuits, so that we can just treat today's transformers when we do fault analysis, really just focusing on those two values. Excuse me. Questions on that?
I just have a question. It's not relating exactly to the question.
the question that we're working on, but, do you know when we can possibly get our tests back to see what exactly, like we messed up on?
Yeah, if Jude wants to let you in my office, they're right there in the office. Like I mentioned in my announcement, I tested positive for COVID. So I'm supposed to isolate per CDC guidelines. I mean, if people want to go in and meet me, I could do that, but that would be potentially all of us setting us up for some trouble here, but can we wait till next week or if you need to get it sooner than later, then I would guess you would coordinate with Jude or John or even Pascal. Okay. Yes, sorry about not getting you back your test, but I couldn't figure out a creative way to get your tests to you without, making it super inconvenient for John and Jude to go ahead and do that. So that's the best I can do at this point. But if it's really important for you to get your test earlier, and if you don't mind potentially being exposed to someone who's tested positive for COVID, I'm happy to meet at some point this week. Just email me. Okay. Any more questions on number one? Reasonable, not reasonable?
It's reasonable.
Okay. All right, number two was a little bit of an interesting one where I tried to get you to think a little bit about how the real world actually monitors equipments. And we talked a little bit about it from a perspective. You don't want to be running 1200 amps into somebody's control house. 1200 amps. I don't know if people have seen that, but that's a lot of current. If you're pushing more than probably 1 to 200 amps, you've got some pretty sizable conductors. And this is, 1,000 amps more than that. So you're talking multiple conductors per phase, or you're talking cables that are without insulators, without insulating material. So pretty big conductors for that. And so one of the things we do is if we have 12,000 amps going through a transmission line, for example, we can actually monitor the current through there using essentially just a regular old transformer. It's sort of twisted a little bit, but what we do is we put this current transformer on there, and the purpose of this transformer is to step down 1200 amps to the corresponding secondary mount, which in North America is typically 5 amps. So devices can be, you can run 5 amp current through some reasonable size conductors. You don't need, 750 MCM and multiple conductors. You can get by with just, typically a number 10 wire is what you would use for CT circuits. And what happens is the current transformer only has, it has 2 windings. Its primary winding is this actual conductor itself. So the main conductor is the primary winding. It's providing a magnetic field. So when we think about windings, we think about something wrapped actually around a core. In reality, all we're trying to do is get a magnetic field that we can link up. So we have magnetic field that is going around that on that wire. That is picked up by this secondary winding and drives it that way. So this transformer has a turns ratio. Oh, I'm not sure why that's doing that. I'm going to try to clean this up. So the turns ratio here is equal to 5 over 1200. Now, the reason why it's not 1200 over 5 is it steps the current down from 1200 to 5, but that's the inverse of the actual turns ratio, which would be stepping the voltage up to a higher level. So this actually steps the voltage up by this ratio, but that's okay because the voltage drop across this transformer is going to be very, very small. So that's why it's asking the question, the voltage drop across the load is 50 volts. So if I have the load, which is on the secondary, is equal to 50 volts, and my turns ratio is primary to secondary like that, if I want to get this value here, then I have 5 over 12. I'm just gonna go, for some reason, I'm getting some real problems, so I'm gonna go ahead and switch to whiteboard. Because it's giving me. Why isn't whiteboard running? Just started it. Before class, sorry about that. I had whiteboard running and it's not running. I'm not sure what happened. Because for some reason, Adobe is not representing things correctly. So let's go ahead and draw that again. Here is 1200 amps. Here's 5 amps. The voltage drop across whatever is connected to the secondary side is 50 volts. So V secondary is 50 volts. And my turns ratio is 5 over 1200, which is V primary to the V secondary. So 5 over 1200 is equal to V primary over V secondary. Okay, or I should say just, I'll just do, sorry, I'll do over 50. So VP is equal to 50 times 5 over 1200. So you can see it steps the current down from 1200 amps on the primary to 5 amps on the secondary. The voltage is going to be the opposite. It steps a lower voltage on the primary to the higher voltage on the secondary. And that's how you maintain that constant power. Okay, so that's the first part. And then the second part is what is or how much power does a transformer draw from the power side? You could do it this way. It's VPIP, which is the same as VP or VSIS. And that's it for question number 2. Questions on that? Most people seem to get this one right. I'm sorry, go ahead.
No, I'm good.
Okay. Any questions on that? Anybody else? All right, let's just copy this over and move this into whiteboard because it's not very effective. Okay. Here's number 3. So the first thing we're going to do is find the phase current, I phase. And if you remember, this is a 3-connected Y generator, which means S3 phase is equal to the square root of 3, V line, I line. Well, in a Y-connected machine, my phase currents, which is the current here, is exactly the same as the line current. So if I solve for my line current here, I'm also getting my phase current correctly. So, and a few people did this, and we have to remember, when you draw the equivalent circuit model, here's EA, here's X sub L, and here is RA. Some people put a short circuit on the terminals and did the calculations that way. If you did a short circuit on the terminals, that's actually a fault condition. The generator is not designed to continuously handle that much current. That would be sort of an extreme case when you have a fault right on the terminals. What you have is you have a load, right? It says a 950 kVA is connected. So instead of drawing a short, it's better to draw 950 kVA at a 0.85 lag power factor. So to solve for your IL, all I needed to do, 950 kVA, whose angle is cosine -1 of 0.85. That's going to be equal to square root of 3 VL IL conjugate. Got the conjugate here, sorry about that. Solve for IL. Now, before I go too far, is this a plus or minus cosine here that's associated with S?
Positive,
Why is it positive?
because it's, since it's a lagging power factor, the current will be lagging.
Very good. This is voltage. This is current. And when I run that through my S equals VI conjugate, I end up with a positive theta. So that's a positive angle. So my IL is equal to 950 kVA at an angle of cosine inverse of 0.85 divided by the square root of 3 times my line voltage, 4.17 K. And because we need a reference point, we make that at an angle of 0. And that is the answer for that one. So this is sort of harkening back a little bit to what we did in the first chapter or the first prelim, but it's important to go ahead and actually calculate the load. We'll be doing that extensively when we do power systems analysis, is what's the load going to be. Excuse me. Questions on that? Okay, part B was the air gap voltage. Once we knew the current over here, here's I, then to solve for EA, we took our terminal voltage, which remember, this is the machine is designed to provide, or what the customer expects, I should say, is rated voltage at the terminals of the machine. And EA is adjusted by varying the excitation so that we meet the client demands of getting 4.17 at an angle, or we pick an angle of 0, but the magnitude of the voltage is going to be 4.17. So my EA is going to be equal to 4.17 K at an angle of 0. Keep in mind, though, this is Y connected, so this has to be divided by the square root of 3, divided by the square root of 3, plus my current IL times RA plus JXL. And if you remember, one of the things that we did towards the end of last week, sorry, is we looked at this and we said, here's our phasor diagram. And remember how we said that if it's a synchronous generator, our terminal voltage is here. And if it's a synchronous generator, we know that our EA value is going to have a positive delta. So your angle had to be positive. And then the other thing that might be subtle is because it's operating at a lagging power factor, what's the direction of reactive power in or out of the machine? With a lagging power factor. We have our power triangle right here. So what's the direction of power? If P is positive and it's a generator, it's out. Is Q a positive number? Not a hard question. It's positive, isn't it? So it's out of the machine. So if P and Q are both positive, we have the positive angle because of the power out. And then the Q, which means it's an overexcited machine, it's providing more reactive power than what's needed from the machine. So if you recall from our phasor diagrams, the magnitude of EA is going to be greater than the magnitude of BT. So another way to check that is to look and see what my magnitudes of the voltages are and see if I get reasonable results. And that was it for number 3. Questions on number 3?
No.
Fair, not fair? Very quiet. Were there any issues with them? I need to know now, or not now, but I need to know so that I can make adjustments for the third test.
That question is fair.
Did everybody feel like they were prepared for it?
Yeah, that question I felt pretty good on.
Okay. Good, because, again, we did a lot of the modeling with the synchronous machine stuff. So hopefully it was one of those ones where it seemed like it was reasonably, or it was reasonable of what you would have expected. So, okay, so let's move on to number 4. Number 4 was, it really didn't matter that it was a synchronous motor. It could have been a load. It doesn't necessarily need to be anything more specific than it was just a load with this certain power factor. So let's go ahead. And the first part was part A, which is, what's the input power? So A was, what is P in? Well, P in is a way to get that. We know efficiency is P out over P in. So P in is equal to your output power over your efficiency. Now, one thing I would say is this is better to convert that to kilowatts, because electrical power would be input power for a motor. So we have to calculate what the demands are in terms of watt, and the output power is more interested for our mechanical friends. So they would do things in terms of horsepower. So that's why horsepower is the output, but the input is kilowatts. So to get this one, it's 25 horsepower times 746 watts per horsepower. And we divide by 0.92, which is our efficiency. For part B, the input kVA, so I'll call this S in. We just saw the power triangle. So we have P in. Here is S in. And oops, I did it leading, so I have to do this the other direction. Sorry about that. So here's P in. And because it's a leading power factor, my S in is in this direction. It doesn't change the magnitude, but it does impact the angle. So my power factor is P in over S in, which implies my input power is equal to my input kVA is equal to my input power divided by my power factor. If you wanted to add the angle, you could have just done that over here, and its angle is equal to the inverse cosine of 0.8, and it's a negative number over here because you can see that's going here. And if that gets confusing, the best thing to do is draw your phasor diagram with voltage and current. And then when you go S equals VI conjugate, you end up with that. Okay. Questions on that? Fair, not fair?
Fair.
Do you feel like you were well prepared?
Yep.
Okay. Okay. Can we move to number 5? Let's copy this over. So number 5 seemed to be the most struggles. Anybody want to comment why?
I personally practiced with a graph, so I wasn't prepared as much for this Even though it was a suggestion problem, I just didn't do this one.
Okay, yeah, that's what I was gonna say is. If you look at. Homework number 4, it's this problem right here, it's problem number 3. So I wasn't trying to be sneaky, I was just saying, it is a problem that they would have seen on suggested problems, so if they would have done it, it might have prepared them. But I guess the general thing is that we don't quite understand how to do this problem, so what it requires is maybe we look a little bit more at the characteristics, the different types of curves for a generator or a motor, doesn't matter, it's a synchronous machine. So if we have our curve here, here's my field current. That's what we learned in lab, that the independent variable is field current. And then on this side, we'll call it voltage. So we can start off by looking at the air gap line, because the air gap line is just a straight line. That's what the voltage is going to be, regardless. There's no saturation involved with that. So it has a constant slope. Okay. The open circuit data it follows that line, but then it starts to experience saturation and then does one of these things. Now we can put another axis on, unless they're really clever like we saw in class. This here is my armature current. And I have a short circuit characteristic that does something like this. And that's a straight line as well. This has a constant slope. There's no saturation that affects that. So this is the short circuit characteristic. This is the air gap line. And this is the open circuit characteristic. So remember, in all cases, right, if we neglect our value of R, here's EA. And we're just going to go ahead and put a JXS here. What we see is XS, not sure why it's getting so ugly like that. XS is going to be equal to EA divided by IA. I don't know why it's getting really sloppy. It's like the line's coming across it. So here's EA and here's IA. So you have to go ahead and solve for two XS's. There's an XS unsaturated and an XS saturated. Okay. So this EA has to be an unsaturated value. And this IA, it doesn't ever saturate because the short circuit characteristic doesn't saturate. Over here, EA is our saturated value. And again, here is our IA. Now, the key thing is that the EA and the IA have to be at the same value of field current. Okay. So let's go ahead and let's take a look at some of the data so that we see the air gap line. Let's say that this is 480 volts. And this here is 480 volts. On the open circuit characteristic, we see that our field current is, I don't know why it's just being really sloppy. It's like the pen isn't working. So for the open circuit, this field current is 16 amps. Don't forget, dude, this is a Y connected machine. So we've got to go ahead and put the square root of 3 over there. And with that, we also know that this short circuit characteristic at 16 amps, it tells us that that current right here is 451.76 amps. That's the first bit. So we have our open circuit characteristic. We have our short circuit characteristic. Whoops, I did this in the wrong spot. I apologize. That is, oh no, this is fine. The air gap line value, this one right here, is 14.7, right? Now let's go ahead and continue the short circuit line up, because at 21.3, we have 601.4 amps of current. Okay, so I know this current value. I know this current value, I know this voltage, and I know this voltage. So I need to get the unsaturated values, the saturated values those are pretty easy because this point right here, I have a current to calculate. So this one is 480 divided by the square root of 3 divided by the armature current at that value, 451.76. For my unsaturated value, I have a voltage here because remember the air gap line is when there's no saturation. It just continues on in a linear progression. I don't know that current, right? This is a question mark at this point. So any ideas how to solve for that question mark? Remember, this eventually gets down to 0 here at some point. How do you solve for the question mark?
Calculate the slope of the short circuit line.
Exactly. Y equals mx plus b, right? B is equal to 0, so that goes away. So if I know the slope of the line and I want to calculate what y is equal to at 14.7 milliamps, I have to calculate the slope of the line. So the slope of the line is 601.41 minus 451.76. That's the rise over the run is 21.3 minus 16. And then when I multiply that by 14.7, I get a value of EA that is unsaturated. And then my EA unsaturated divided by my 14.7 is the answer I'm looking for. Questions on that?
Might be on the concept as a whole, but based on this chart, which may not be to scale, isn't even at 14.7, isn't the generator motor still saturated?
Well, like you said, it's not to scale, right? But the assumption is you would actually have to be further down here to get that value.
Okay, so the
It's a
air gap.
constant slope, right? So this
Right.
X value would be a constant slope. So even though it looks like this point is over here, this still is for its unsaturated characteristic because the slope of the line is constant. And remember, the slope of this line is essentially X. It's constant that whole way.
Right. So the assumption should be that the air gap values would be somewhere on this constant part of that.
Right. Exactly. Yep. Questions on that? Or more questions? Fair, unfair?
I just want to make a comment because I thought when we went to the study help session, I could be remembering wrong, but I thought you said if we had anything with unsaturated, saturated, we'd have a graph and not actually have to make said graph.
You didn't need to make this graph. This is just the understanding about doing the plots. I mean, not doing the plots, but getting the slope. It helps you
But I mean-
understand it. I'm sorry.
I mean, like, if we were to have a question on the test, I thought you had said that we wouldn't have to make this graph to make that understanding. We'd be given a graph to interpret and not just the plain data.
I thought what I said during the study session is you're going to be given, you'll be given enough information that you won't have to pull points off a graph. Is how I
Okay.
said that.
I must have misinterpreted that. But also, I just wanted to point out that at least on the study guide, I kind of re-skimmed over it and I didn't see. I know it wasn't one of the suggested homework problems, but it wasn't on something that I had completely prepared for on the study guide, according to the study guide.
So let me look for the study guide. It says problem E, given test data, find synchronous machine equivalent parameters. And under section 9.
All right, I see that. Yeah.
Is that? It's actually not section 9, right? You can see that this is at the end where it's just a specific test question, so it's not necessarily with section 9. This is. So that wasn't clear?
I mean, it might have just been that I kind of looked over it too quickly, but I would have rather like a specific, like finding unsaturated, saturated, like that spelled out. But that's just me and what I'm used to. So.
Okay. Does anybody else share Chris's concerns? Or comments, I should say?
Kind of in the same sense, yeah. I feel like as much, I always look at the specific test questions at the end because I know that's kind of from the previous exam, that's kind of be the guidelines that were given. But for some of them, I'm still kind of guessing as to what the problem's actually going to be about. Like I understand you give us the general idea, but trying to figure out what problems to look over and what concepts to kind of review for those specific problems, I feel like at least I struggle with.
Are you saying that the specific test questions are too, the detail is too generic?
At least from my understanding of it, yeah. But I don't know if other people share that opinion. That's just my personal troubles with it.
Okay.
Yeah, no, I'd say the same thing. I know it sounds dumb, but like to spell it out is a lot easier than me having to figure out. Like I'd like to know exactly what type of stuff is on the test. Like maybe I should have done a better job studying to figure out those equations, and they would have very much helped. But that's just me. Like spelling it out gives me at least an ease to know that I can look at the study guide and see exactly what I need. So that way I'm not guessing, do I need this information? Do I need that information? But I do understand that on your behalf that those take work to put stuff into a study guide. But at least that would help me, and that would help anyone else if we had stuff like that. Even like a simple like basic equations, like that would be useful. I think that would make like a very world of difference when it came to actually doing the test.
Okay. Well, so the equations that I include and the concepts I include are sort of the newer concepts that we've discussed. So a lot of the equations that we've done in here are just like this equation, E divided, that's just Ohm's law. So I don't put those type of equations back in there because it's stuff that perhaps you've already seen or are accustomed to. And then the only other thing I would say about the feedback is, remember, the test is just a tool to assess if you've learned. I'm trying to write something generically enough so that it demonstrates understanding. I don't want to give tests just to see like if you can do these specific questions, because the understanding of the material is important. So I can't say here's the problem A, B, C, D, E, and then that just shows that you can do those problems, but it doesn't necessarily show that you understand the concept of the material. So I can't get too specific, but maybe I can see about adding a few more equations in there. But I thought the equations, that's the other thing too, is if I went back to like on this previous problems where I did power triangle stuff, whoops. If I did power triangle stuff, like that would be, I could do that on every test. The same thing with square root of 3 versus 3. Those are previous material that if I just added them to this, it would be, 20 pages long to the study session. So I guess if we can talk more about that, maybe as we're preparing the next study guide. And Chris, if you'd be willing to help out, you could perhaps give me some guidance saying, okay, here's what I find, here's some of the equations that I think are useful. So maybe you and I can work together a little bit in terms of what you feel are the key points of each section. And then I'd be happy to include that. I don't mind putting the extra work. I don't know how much detail to get into before it gets to be, a bit much. And keep in mind, the exam 2 review was 4 pages. There's over 1,000 words. And at some point you get to have so much material that people just tune you out. But yeah, if you want to give me some guidance on what additional stuff to put, that'd be very helpful.
Yeah, of course.
Yeah.
I thank you for that sentiment. I don't know. I go by the idea of I'd rather be over prepared than under prepared. But
Okay.
yeah, we can talk about it.
Yeah, thank you. Okay, the last part on this one is the short circuit ratio, and that is my field current at, let's see, what is it? It's the field current at rated So IF at rated I think I have that backwards, rated voltage. And this is IF at rated I. And when you plug those in, that one was about 75%. Okay, any more discussion on number 5? So you feel like it was fair, but perhaps more detail in the study guide. By putting it as a suggested problem, was that not helpful? Do people think that that wasn't helpful?
I mean, if it was like I said, if it was a suggested problem on the study guide, then I would have it would have been more on my radar.
Okay. But having a suggested the suggested problem in the homework, that wasn't enough to get you to work through the material.
I mean, it could have been if I just put a little more in, I guess, but at least the way I did it this go around, it just kind of flew a little more under my radar.
Okay. What's the general consensus? Are people doing the suggested problems?
I did look at them, but then again, just with like some of the being out of class and stuff with the health issues and whatnot, I wasn't able to. I guess I could have reached out over email now looking back at the situation, but I had some trouble with a couple of them and I just didn't get the chance to ask, but I should have reached out after class, so that's on me.
Yeah, I'm, Zoom works really well. I've met students on weekends and stuff like that. I've just been surprisingly sick this semester. And I'm not exactly sure why that is, but hopefully next week I'll be back and won't have any more sicknesses. But yes, please feel free, because if people email me and check in with me all the time, and I'm usually pretty good about responding. Yesterday was pretty much of a bad day. I had chills almost all day yesterday, so I was pretty out of commission. I'm not feeling great today, but still stomaching through. So, but but again, the question is, are people doing the suggested problems, or should I make them mandatory?
I do some of them.
Okay, would it be better to make them mandatory?
I definitely look at them and try to work my way through it. But since the answers are there, obviously I'm just trying to see if I can get the right answer. And if I can't, then I just get a little lost, and that's where I was gonna ask the question. So I guess like seeing the workout and stuff that I get confused on is just something I gotta speak up about. But do you post the work for the suggested problems, or is it just the mandatory problems for the homework solution?
I just do the mandatory problems. The suggested problems, I just give you the answers. And the reason being for that is, if you have all the answers and all the work done out, it doesn't encourage you to check through and to see that you can actually do it. And so hopefully doing the required problems, if you struggled on a suggested problem, you can either spend more time practicing the concept, or you can come see me and then we can hone in on understanding the concepts. But it sounds like I should make those mandatory. Is that what people are asking for?
I think, or at least like Austin was kind of getting at, where it's like, if it is going to be something that's on the test, have the work done out. Like I completely understand your view that like, if there's work done out, then we're not going to look over it and try to understand it. We're just going to kind of copy paste it and hope it works. But maybe I'm in the minority in that sense of, I do use that work to be able to help me understand the concepts, because there might be something that we might not have gone too much in depth in, and seeing the work done out to be able to understand and understand like how certain points are reached or how certain equations were gotten to, like that helps me understand the concept a lot more than just getting the answer. And if I don't have like some form of like instructions, if that makes sense, like via equations or via work, to understand how that was gotten there, it kind of deters me from figuring out on my own just by myself, because it gives me less resources overall.
Okay. So it sounds like what you're saying is keep the suggested problems, but you want the full worked out parts for it too.
Yes, especially if it is in the end going to be on the test.
Well, that's just it. I don't know if it's gonna be on the test or not. I can't always,
Well,
go ahead.
Well, I mean, yeah, in that case, if you don't know, it's always gonna be on the test, like I said, over prepared rather than under prepared, so it would help to have the work.
Anybody else have thoughts on that?
I think the equations for the suggestion problems, that's a good idea. I know that a couple of us were asked, if we knew how to do that one the day of the test. I didn't know how to do it personally. I looked at it and I saw the answers, but I wasn't sure on the equations. So I think if those are there, that obviously would help me out on the test, but that's just that one question.
Well, that's a suggestion too, is that if anybody gets stuck, that, we had that kind of quote unquote study session. And I don't think anybody asked any questions on that particular problem. So I just assumed everybody understood it. That's why I didn't go over it. So, okay. All right, well, thank you for the feedback. So it sounds like, and I'll try to get some of the work done for the suggested problems. Okay, last problem. Problem 6 is we have 3,600 RPM. The first part is convert to radians per second. So 3,600 revolutions per minute. There are 2 pi radians per revolution. And there is 60 seconds in a minute. So cancel, and what you're going to end up with is radians per second. If you looked at that table, you would have found the answer was 377, which is the same thing as omega, right? Omega that we talked about is just 377 radians per second. The next one is if it's converted to a 50 hertz system, what would the new rotational speed be? Well, remember 60 hertz equals 3,600 RPM. You could have done it and said, well, 50 hertz to 60 hertz is a ratio times 3,600 RPM. That's one way to do it. You also, if you don't remember, so that's just a practical way. The actual equation is the frequency times 120 over the number of poles. The only hard part about this is when we have 3,600 RPM, you need to know what the speed is. Well, we talked about if it's a 2-pole machine, it runs at 3,200 RPM. So P was going to be equal to 2. And that's the test. Any overall thoughts? Because the average was a 74 for the test. No comments or discussion? I mean, like I said, we're trying to learn. On the first test, we made some adjustments, and if we still need to continue making adjustments, it sounds like I need to add some more stuff on the suggested problems. But if there's other things, and I'm going to work with Chris, so thank you for helping me with that in terms of what would be important content to add for equations. Are there other suggestions? I mean, again, going back to the tests, I know a couple of people said it was fair. Did you feel like you were prepared? Again, me being sick, and I apologize. I missed a couple of days and I tried to do the classes, but I've been trying to make up as much as I can. And then this week has just been a bad week because of COVID, but otherwise than that, I'm trying to make it up. So if you have other feedback or comments, how we can do better and how I can help you learn this stuff, that's important for me. So,
I mean,
Yeah.
overall, I think it was a very decently fair. It was just, at least for me, it was 4 and 5 that I kind of struggled with. And because 5 was worth 30 points, and that was the biggest one I had trouble with, that kind of screwed me in the end.
Okay. Okay, thank you. Anybody have any other thoughts or comments? Okay, well, I'm gonna go in class because I'm having a hard time breathing. And I have another class I have to do at the next little bit, but otherwise than that, thank you very much. And like I said, feel free to reach out to John and Jude and see if they'll I'll get you the test, but if not, I'm supposed to quarantine or isolate, I'm sorry, for 5 days. 5 or 7 days, I can't remember exactly what it is, so hopefully I'll be back on campus on Monday. But with that being said, thank you very much. And I will hope to see you all next week. Take care.
Thank you.
Thank you.